All right, so this is computer architecture and organization, and mostly assembly language here. And we're down to talking about 64-bit x86 assembly. Well, yeah, the news is pretty upsetting. We're in a bad state politically. But anyway, let's start to talk about this, and then I'll do some demonstrations, although not the demonstrations I planned on doing, because there is some strange problem I haven't figured out yet. But anyway, all right, so for 64-bit assembly, we're just going to talk about it, and it's going to follow the same discussion that we did with 32-bit assembly. It's very similar. Once you know one, the other is very simple. So here's an example of an adder where you have a main function that defines a variable x and then calls adder2 of x. An adder has a single parameter called a, and it returns a plus 2. So there are no local variables in adder2 at all, so it doesn't need any room on the stack. So I should have that here and compiled. Let me clear and get this thing to work. All right, and go up here and up here. All right, and let's make this bigger. All right, so I've got this live, presumably. Let me cd. All right. And so I should have adder2 and adder2 64. So I've already compiled it. If I cat adder 2.c. All right. So there it is. All right, so that's the function I just described, and I've already compiled it. So I have adder2, 64. All right, and so it gives me the answer 42. And the interesting thing is, how did it do that? And I think we're going to get it with objdump. Yep. So objdump minus d will show you the assembly code. And I think it's called adder2. 64. All right, if I do that, here it comes. So here's the main routine, and adder2 is up here. So you can see how it works, and you see it's exactly the same as this. You can even compare the byte by byte and see they're exactly the same, which is nice. So this is what prepares the stack frame. It pushes the base pointer from the calling routine onto the stack, which will be used to return to the correct stack frame when you return. And then it moves RSP to RBP. And by the way, this is AT&T syntax, not Intel, where the source is on the left and the destination is on the right. And I can tell because here it moves 2 into EAX, and it can't possibly move anything into 2. So that's supposed to be the source. So it moves RSP into RBP, which creates a new stack frame starting at the next available word on the stack. And then it moves EDI into RBP minus 4, which is up where parameters live. And I'm a little concerned, moved EDI into there. Seems like it should be going this way. Same thing there. I'm a little confused about this. Why you put EDI up there when you haven't even defined what EDI is. Oh, yes, I think I know. In 64-bit functions, the parameters come in the registers. So various registers carry them in. So EDI must be what's moving in this parameter, 40 that came in. Okay, I remember now. I forget which registers are used, but when you pass a register to a parameter, when you pass a parameter to a subroutine in 64-bit assembler, it passes it in the registers, not on the stack. So this EDI must be a parameter coming in, so it puts it in a location relative to RBP, which, and then it puts that in EAX, and then it adds 2 to EAX and returns, because EAX is used for the return value. So this works. Now, what's interesting to me is it uses this location, minus 4 RBP, as if it was a local variable on the stack, but it's not. So I guess it just uses that area above the stack frames as a temporary scratch pad which is sort of odd. You know, I would think if you're going to use that data, you should decrement ESP and allocate it as a local stack frame, but they don't. Anyway, it'll work. I guess it's harmless. I'm just a little surprised that the compiler made this decision. I would have used a register for this, a place where I know I can put in temporary information. I wouldn't use a location in memory for that, but that's what they did. So anyway, that's one of the many ways to accomplish it. And this points out something that you should understand. When you write C, it's like driving a car with automatic. You don't really know what the assembly code is going to be. And there are different versions, and there are different levels of optimization. So the question here, it somehow has to store this parameter A, and somehow add 2 to it. And how it did that, there are various ways it could do that. And the compiler could, in principle, do it in different ways. If you don't write your own assembly code, you don't really control it. So anyway, 64-bit Intels have 16 registers, all starting with R. They're all general purpose, but RSP and RBP are the stack pointer and the frame pointer, just like ESP and EBP in 32-bit. ESP is the top of the stack, the next available word to use, and EBP is the bottom of the stack frame, and it's the same with RSP and RBP, and RIP is the instruction pointer. So you can also refer to lesser than 64 bits at a time if you want to. If it starts with R, you get the 64-bit. You can use E to do the lower 32 bits, or the lower 16, the lower 8 bits. So it's backward compatible in that regard. You can run code that uses 8 bits at a time if you want to, although there's usually no reason to do that. And all the registers have this ability to look at smaller pieces of them. All right, so here's an instruction, add 2 to RAX. That was part of that function we just looked at. So the opcode is add, the operands are 2 and RAX. Literal values are preceded with the dollars. So that's the literal value 2. Registers have a percent RAX, and memory locations have parentheses to indicate them. So this is going to take the value in RBP, add 8 to it, and go to that memory location. So that's a pointer dereference. This will read or write from that memory location. All right. And this is an immediate memory address. All right. So here's some examples. There's a register. There's a memory location where what's in the register, you look it up. Here's an immediate constant. And this is memory. I guess by just not having the dollars is enough to make it a memory address. It doesn't have to have the parentheses. I'm used to having brackets. I think that is Intel syntax. But here, if it doesn't have the dollars, then it's a memory location, so that's interesting. And here you've got 8 added to RAX, so that's going to be a memory location. And here you've got a memory location, RAX plus RCX, so you locate it. And here you got RAX plus RCX plus 4. And here you've got the one where you multiply it by putting an extra comma here at the start. We did this before. You mean start at this location and then multiply these two things together and go there. And this is how you count by 4 or 8 bytes at a time to page through a large area of memory, one word at a time. And this word has to be 1, 2, 4, or 8, the only values allowed here. All right. So that's very much like what we did before. So you cannot write to a constant. That's what I mentioned. That's why I always do that, to try to figure out whether I'm in Intel or AT&T format. I look for a constant, and then I know that must be the source. And you can't use memory for both source and destination. I don't know why. That's just the rules of Intel. And like I say, the scaling parameter has to be 1, 2, 4, or 8. Nothing else is supported. And then you can have suffixes which tell it how much data you're applying to. So B is a single byte, W is a word, which is 2 bytes, L is 4 bytes, and S is 4 bytes for floating. Here's quad, which is 8 bytes, and D is another version of 8 bytes. So you might see these suffixes on commands to specify how much data that one command is supposed to affect. All right, so move is the most common instruction. In fact, it's all you really need. There is a compiler that compiles everything down to just move instructions. You can imprint, it is MP complete. You can totally do everything in move instructions. But it's hard to read, so people don't like it. So this moves source to destination. This adds source to destination. This subtracts source from destination. And in all cases, it puts the answer at destination. You can push stuff on the stack. You can pop stuff off the stack. And this will move 64 bits on the stack and off the stack. Each instruction moves 64 bits. which is the point. That makes the processor faster. So we can play with adder2. We already looked at this. It has no local variables. And so we can look at it in the debugger. Let's try that. Let's clear. All right, and GDB, all right, clear. All right, so GDB minus Q adder 2. Oh, I wanted to adder 264, I bet. Yep, okay. Let me, there. All right, get out of here and put in 64. All right, and let's get rid of the colors because I can't see anything. Whoever put colors in a Linux terminal, I wish they would have knocked it off. Break star adder 2. Oh, I forgot. I didn't get the star. That's why it's not tab completing on me. Okay, now it's tab completing. All right. So it'll break at the entrance to the adder2 subroutine, and now I can run it. And it's going to start. All right, and here it is. There's the breakpoint. Notice, by the way, this 64-bit address, starting with some zeros, then having a lot of 55s and a number at the end. That's typically where code goes, is starting with 55 and 4 zeros. That's where it puts it for the text portion that contains the assembly language instruction. So now we can disassemble adder2. All right, and there it is. We've seen this already. Here's the add2 and so on. Now we can look at the registers. There are a lot of registers. You can see RAX has 40, RDI has 40, and that's what I was wondering about. This move, EDI up there, that's RDI came in containing the input parameter, 40. And by the way, here's another strange thing. It only moved 32 bits of it up here, which I guess is because of the variable type. Let's take a look at the C code, which is back here. Yeah, it was an int, and I think that's right. I think an int is only 4 bytes, even in 64-bit compiling. That's why it did that. It came in as a 4-byte variable, so it preserved that. It moved only 32 bits up here and worked that way. All right, and down here, it moved it into %EAX. This is also a 32-bit instruction, and here it added 2 to %EAX. So I was surprised to see this. You see, this is a 64-bit register, and this is a 32-bit portion of the register. So since the variable was a 32-bit integer, it did the assembly language calculation at the 32-bit level, which is pretty nice. All right. All right, so EIP. All right, let's see what we got here. RIP. Points to the start of adder2 here. You can see it. This is what it's telling you. Starting with 5555, that is the start of adder2. And that's because we just did the call to enter adder2, of course. That's what we did. We put a breakpoint there. So you see this little arrow here tells you we are right now there, just about to enter adder2. So the first 2 commands are the prologue, preparing the stack frame, which is a stack frame of size 0. This is the epilogue, which restores the base pointer and returns to it. A quick question. How do I determine whether the register is 32 or 64 bits? It's very easy, and I'm glad you're asking. You can tell if it starts with R, it's a 64-bit register. If it starts with E, it's a 32-bit register. And so let me go back to the slide that showed you that. That's a very good question, and we had that all back up here, but there they are. So here you are. This is the one. So RAX is 64-bit, EAX is 32, AX is 16, and AL is 8. That's what you'll see. Another thing you might see is a suffix on the command, but I'm not seeing that here. But I am seeing just the register itself tells me. And you do see strange things like this, where I take an address, which is 64 bits, and I use it to get data, but I only use 32 bits of that data. So that's interesting. This combines 64 and 32-bit instructions, bits of data in the same command. All right, and so before entering this adder function, you can see the stack frame. So if you go up here, RSP and RBP, here's the top of the stack frame and the bottom of the stack frame. So as you can see, it has a size that's not 0. It's 18 in hex, which is 24 bytes, 16 plus 8. So that's because this is the stack frame of the main function, not the adder2 function. We've just moved to the beginning of adder2, but we have not yet created the stack frame on the adder2 function. So let's do that. That's the prologue. And so we'll just do two next dies, do next instructions, and the next instruction again, and then disassemble adder2 again. And you see now we're down here. So now we have executed the first two commands, which create a new stack frame. So now if I run info registers again, now RBP and RSP are the same. I've created a new stack frame at lower memory than the other one, memory that's not in use, and it's of size 0. The previous stack frame went down to 348. And remember, it's 8 bytes now to store anything. So 348 refers to the 8-byte word starting at 348. So the next available stack frame below that is 340. And that's where we are. The start and end of the stack frame is at 340. It's of size 0. All right. And now we can examine it. X, 12X. Oh, that's kind of a screwy thing to do. I think it should be RSP, not ESP. There, we can look at the stack frame, and the top of the stack has the saved base pointer to return, and that's what this is, all 64 bits of it. And then it has the return pointer here, all 64 bits of that. And there's no local variables. So this is the saved RBP, and this is the saved RIP, which will be restored when we return to the main function. All right. So the epilogue will release with pop and return. Pop will restore the RBP that was saved, and return will pop the RIP off. That's what it does, and go back to where it was, back to the pre-calling function. So that's the game. All right. So there's more arithmetic instructions, of course. There's add, subtract, increment, decrement, negate, multiply and divide, integer, multiply and divide. There's shift arithmetic left and shift arithmetic right. And there's logical left and logical right. And I think the arithmetic one is the one that preserves the sign bit. And the logical shift just moves all the bits like dice without preserving anything. All right. And so here you also have bitwise operators, like do an bitwise AND, which means both of the bits have to be 1 for the bit to remain 1. So this is bitwise source and destination. And here you got an OR, so if either one of the bits in each pair is 1, the answer is 1. Here you have exclusive OR, so only if exactly one of the pair of bits is 1 is the result 1. And here you have NOT, which flips every bit. All the 1s turn into 0s, and all the 0s turn into 1s. Those are instructions that are available to you, of course. And this is the thing about C, and to some extent assembler. If you're a real wizard, you can do really efficient coding by brilliantly using these bitwise instructions. But it's very hard for people to understand. So, when I was a physicist, a young physicist, I would love to do super elite stuff like this to make it really fast. But when I moved into financial work, which was very interesting and very good for my development, I learned to stop being that way and instead make the clearest code that was easiest to understand, because that's how you avoid mistakes. If you get clever and you do something brilliant that's hard to understand, that's a mistake, because you can't understand it later. Other people can't understand it. Other developers can't add on to it. If in financial work you learn speed is not the goal. The goal is accuracy. And this is why I'm always upset about all the cryptocurrency exchanges, like the one that just got hacked for $1.5 billion. I've worked in real banks, and there are a lot of controls to make sure the money is not stolen or mishandled. And these crypto things just set up like servers and software just casually without considering any of that. And they keep getting money stolen, because they don't know how to be careful to make things right. They just make things run fast and things like that. And, it's a whole different kind of education to decide to become reliable and dependable instead of showing off that you're clever. Anyway, there's this weird thing called load effective address. If you want to know what RAX plus 8 is, yeah, let's see, a quote that's credited to Einstein. It says, if I can't explain it simply, you don't understand it. That's true. He's right about that. If you understand anything, you should be able to explain it to a barmaid. That's what Einstein said. And that's certainly true. You should be able to boil everything down until it gets simple. You're right. Some things stay pretty complex, but that's usually because you're not smart enough to make them simple. Remember, I wrote a research paper one time where I had like 10 pages of dense math to prove something. And, you know, people like Feynman were able to think of brilliant ways to do it with like cartoons that made it easy. But I wasn't, so I'd slogged through many pages of hard math to get places. That's one way to get there, but the brilliant people can often find a brilliant way to make it all clear and simple. Anyway, so load effective address will calculate the address of this. So it's going to take RAX plus 8 and put it in RAX, not the memory location, but the address. This seems silly to me. I mean, if I wanted RAX plus 8, I would just add 8 to RAX. Anyway, there it is. You can calculate the address of a memory location and then save the address, not the contents. It's an option, load effective address. All right, so let's try some Cahoots. I should have them. I guess I have to open them, but they should be available. Let's see. All right. And this is Chapter 7, I believe. Yep, Chapter 7A. All right. Oh, there it is. Okay, good. All right. Guess we got whoever's coming. All right. So what's the stack pointer in a 64-bit system? All right, that's RSP, that's the top of the stack. The bottom is RBP, the base pointer, or the frame pointer. It tells you which stack frame you're using. All right. All right, what part of a function reserves space for a new stack frame? That's the prologue. When you enter the function knows how much room it needs for local variables, so it creates a stack frame with enough size to store the local variables. It doesn't expect the calling function to do that. All right. All right, which command divides the integer in EAX by 4? Oh, well, everybody got it wrong. But the point is, if you move it by 4 bits, you're multiplying or dividing it by 16. That's one thing. Every motion of 1 bit doubles the number. So this, in fact, will divide the number by 16 arithmetically. This will multiply it by 4, and this will divide it by 4. You shift it 2 bits to divide by 4. That's an important thing to know. Just like if you have a base 10 number, and you shift it to the left, you've multiplied it by 10. If you have a base 2 number, and you shift it to the left, you've multiplied it by 2. All right. Well, all right, fair enough. All right. That's the thing about review questions. Some of them point out what people don't know. All right, good. Anyway, so, and feel free to let me know if you got a question about those things. Yeah. Oh, that's right. But and as you know, it grades you not only in accuracy but also on speed. So every single question is worth 1,000 points. So you know. All right. Anyway, so then you got conditional jumps and loops, of course. So you can do a compare or a test. I don't remember how they work. I just know that if it's totally 0, they both have the same answer. But this takes the subtraction of the 2, and this does and the 2. All right. Anyway, they do a comparison, and then you have flags that are set. 0 flag tells whether the last calculation resulted in 0, if it's negative, if an overflow occurred, if the arithmetic carry has occurred, that sort of thing. And you don't normally refer to these flags directly. What you do is you use conditional jumps that depend on them. Like this is an unconditional jump. This is go to. It will just go to this new location. But then there's the conditional jumps. Jump if the last thing was equal to 0, jump if it's not 0, jump if it's negative, jump if non-negative, and so on. You have these many combinations of these. So these work on those flags. But you don't have to refer to the flags directly. You do a JZ, and it looks at the 0 flag to decide if the last calculation resulted in 0. And that's goto, essentially. So here, when you have a loop, now, as you know, goto is not recommended in any high-level language. It makes it hard to read code, hard to control it. What you're supposed to do instead of goto is have things like these brackets where you have a block of code and then an if and an else like this, or a while, or a do, that sort of thing. So this is the way you should do it in proper C. You'd say, if x is greater than y, then do this, otherwise do that. But you could do it with goto. If x is less than or equal to y, then go to the else statement. Otherwise, do this one, and now jump to done. So 2 gotos will accomplish the same thing as these 2 sets of brackets. And it is considered much inferior way to program. By the way, there's a famous case I think I mentioned before, the goto fail. Apple had a serious vulnerability caused by having 2 gotos in a row that made what should have been a conditional branch an unconditional branch and skipped over a security test. So goto is considered a poor practice. However, in assembly language, you have to use it. So writing it with goto is the way to understand how it's going to look in assembly language. So here's how it's going to look in assembly code, where I removed the prologue and epilogue just to make it simpler. So here, I move a parameter into the stack frame, and here I move another parameter into the stack frame. So those are x and y, presumably, getting moved into locations on the stack. Now I move one of them into EAX, and I compare the other one with EAX, because you can't compare a memory location to a memory location. That would be nice, but it won't let you do that. Remember a few slides back, you're not allowed to have memory locations on both sides. So if you want to compare this location to that location, you have to move it into a register and then compare the register to the other one. So this comparison will tell me the relationship between those things. And now if it's less than or equal, then jump down here, Otherwise, go here. And if you do this, then jump over that one, so you don't execute it. That's the point. It's because you're going to have one result for one condition of the if and another result for the other condition of the if, and it takes two jumps, an unconditional jump and a conditional jump to add up to this if-else statement. So, all right. So here's a conditional move. There is a command called conditional move, which is pretty cool. This will conditionally move less than or equal. So if the last result resulted in something less than or equal than 0, then it will do the move. Otherwise, it won't do the move. So this is a way to do it without any of those jumps. You set up the variables and you compare them here, compare x and y, and then you do a conditional move. You only move if the condition was true. So you put one value in the output here, and you only override it with another value if the condition is true. So this is another way that your compiler might choose to compile it, by using a conditional move instead of a couple of jumps. All right. And so there are a bunch of these conditional moves that work just the same. Move if equal, move if not equal, move if negative, move if non-negative, and so on. All right. And then you can have loops in assembly. So here's a couple of C loops that do the same thing. While I is less than or equal to n, I starts at 1. You add something to total, then you do I plus equals 1. So I is going to go up every time, and eventually it'll be equal to n. So this will add up all the numbers up to n. That's one way to do it. Here you do it with a for loop, which is certainly what I would do. The simpler way is what it's for. For I equals 1, I less than equal to n, I plus plus, add the total. This is the way I'm used to doing it. But they both do the same thing. And they're both going to turn into the same assembly code, because remember, in assembly, you don't have while and you don't have for. All you have are jump 0, jump not 0, and compare, and those conditional moves. So in fact, they're both going to turn into this. So here we make a new stack frame with the prologue. Here we take the first parameter and put it at E14, at this location 14 for the base pointer. And now let me go back. We're going to try to count all the numbers from 1 up to that. So we're going to have a total starting at 0 and a counter starting at 1. So this is going to put 0 in a variable with total, and here's going to put 1 in another variable. So this is n. So we got the variables ready. So now we're going to jump to this place, plus 33. And there we're going to copy I to EAX, compare it with n, and see if it's time to leave the loop. And if it is not, this will be less than or equal to, so you jump back and do another loop. And every time you do a loop, you copy I to EAX and add I to the total, and then add 1 to I. So you see over here, it shows you what these are doing. So that's what it looks like, and both of those C codes, that's the point I made before. When you write C, you're not really controlling your computer, which is what I said at the start of this class. You know, if you only know a high-level language, you can get things done, but you're not really controlling the hardware. And if you want to be a hacker, you want to exploit vulnerabilities, you really need to get right down in the hardware to find out what's going on. And if you want to work in tight constraints, like an Internet of Things or a game where you're really trying to get the most out of it, if you really want to understand what's happening, you get down here. And by the way, I heard recently that computer science students are still in high demand, whereas people that learn high-level languages are perhaps in less demand because they think they can replace them with AI. But computer science students are considered more valuable than ever because you actually understand the hardware, and you can actually design new things by really understanding what's going on in a way that a person that only knows a high-level language doesn't really know what's going on. They only deal with theoretical abstracts like these variables and these loops, and those are all abstractions. They're simulations. They're illusory things like items in a game. They're not really what's in the hardware. There's no while in the hardware. This is a illusion that's created by the assembly code. Yeah, do compilers make different assembly versions for each different language? Well, the compilers will do whatever the compiler designer made it do, and we're going to get to this later. There are optimization switches. You can control what you want the compiler to do. So, it's going to be up to the development team what they built the compiler is. And compilers have bugs, and compilers have mistakes, and compilers have different versions. So there's not a simple answer. That's why, if you don't write assembly code, you don't really know what you're doing. But of course, it's more efficient to write in a higher level language, so most people do that to get things. But when you have a problem, you really have to get all the way down to the hardware. The same thing's true of networking, by the way. You can connect machines and adjust addresses and Active Directory groups and logins and all that stuff, and that's fine. But when you have trouble, you really want to go back down to Wireshark and look at the raw packets and find out what packets were sent and what packets got there. That's how you figure out what problems are. So anyway, all right. So your functions in assembly, this is how you prepare the stack for leaving a function, and here's how you enter a function. Switches the active frame to the calling function. So this is move RBP into RSP. So you take the, why would you move the base pointer? If you're leaving a function, RBP, right, okay, because the base of the current stack frame is the next available word at the end of the previous one. This is right. So the new RSP is the RBP of this stack frame that's available for reuse. And then you pop the old RBP up. This will create the situation the calling function expected, where it has the base pointer where it was and the stack pointer pointing to the top of that stack frame. That's what this does. And here's when you enter, this is going to push the instruction pointer and move the address of the function into the instruction pointer. This is what the calling function does. It saves this is the return address that we've been attacking in the buffer overflows, and this is the action that moves into the RIP, the address. So you move to execute commands in the calling function instead of the function that's calling it, the called function. And here's return Q, returns towards the active frame, and that's pop RIP. That just moves the instruction pointer to the saved return pointer to go back and resume. So that's what you see here. All right. And so you got parameters, and this is what I was mentioning earlier. The parameters go like this. First one in RDI, next one in RSI, and so on. Notice that you don't use RAX because RAX is used for the return value. So the parameters are what's used, the registers what's used for parameters in the 64-bit system. In 32-bit system, they go in memory above the stack frame, or I guess at a lower address than the stack frame. And but that's because there aren't enough registers in a 32-bit system to use them this way. In a 64-bit system, you have a lot of registers, so you can use them for this purpose. All right. And so let's play with adder. Now here's the one we had before, where you have two functions. You have adder and assign. So you call assign, and assign creates a local variable that's 40 and returns it. And then you return to the main function, so this stack frame is released. Then you call adder, which is going to add to a local variable, a plus 2, but it never assigned anything to that local variable, so it's going to have this leftover value on the stack from before, a data remnant, so it's going to end up with 42, even though the developer didn't actually intend any of that here, but made a variety of mistakes that lead to here. So it's adder 64. I've got that already compiled. All right, so let's play with it. Let's get out of here. I think I'm already doing it, but let's debug it again. Yeah, GDB minus Q, adder 64, not adder 2. Okay, there we are. Now break into the assign function at the start of the assign function. And while we're at it, break at adder. Okay, now I get rid of the colors, good, which I make it hard to see. And now run. Okay, so run is going to run the main function and then call assign. And that gets us into the assign function. You see here we are at the 64-bit address at the start of the assign function. So now I disassemble assign. All right. And so here we are at the start of it. We haven't entered yet. And we're about to create a stack frame here and then move something out of the stack. So we can examine the stack, an area around the stack, x16x. Let's look at instead of doing info registers, which would print out all the registers and sort of fill up the screen, I'm going to print them one at a time because the only ones we care about are RSP and RBP. All right, and so this is from the calling function, so it goes from 348 to 360. That's the main function. which called this assign. And we can examine an area of memory around that, around the newly created stack frame here with RBP minus 0x30. All right, so there's a region of memory here, which doesn't have anything particularly interesting in it right now, but I do see a stack address here, a 64-bit stack address, and this is a address in the text section with all the 55s. That's probably a return address, and so on. So now let's go down here. All right, so now we're going to do 4 commands in here, next I, and disassemble assign again so we can see where we are. All right, now we have moved down to here. So we have moved 28 into a location on the stack, and we have moved this data into EAX. So this is what put 40 into a variable, and then we're going to return that variable, which is what this function does. So we can examine that stack again. We can look at the stack frame, print RSP, print RBP. Oops, let me do it. Print RSP and print RBP. There. Okay. And see, once again, this function has no local variables, so the stack frame is of size 0. And yet, we did write some data to the stack. And in particular, we wrote 28, and there it is. That was not there before. Really, this is the same, 340. Yep, so that 340, that is on the 330 line. The 330 line used to have a 0 there. Now it has a 28 there. So we've written this into a local variable, into where the parameter was. So let's go back to the source code and understand this. This function defines a local variable of 40 and returns it. So actually, the thing that surprises me is why didn't it create a stack frame with enough size to store that local variable? It didn't. The stack frame is of size 0. I don't completely understand that. I would expect the stack frame to be big enough to hold the variable. When you do this and have a variable, I expect that to be in the stack frame. And this reminds me of the last one where I also saw it using data beyond the stack frame as a temporary storage space. And I think what's going on is the compiler is smart enough to notice that it doesn't do any math on this, and it just returns it. So it doesn't really need to store it on the stack frame and use it over and over. It just needs to store it long enough to return it. So instead of making a stack frame, it just stored it in data beyond the stack frame, which is not going to have to be returned. So this just seems to be like a compiler optimization to save some time. I think this example does have an error in it. The error in it is at the C level. The error is that when you called this function, adder, you forgot to send it a parameter. But it's going to find a parameter left over from previous function. I'm just noticing that, you know, the way the compiler created this code is a little strange. It uses an area without, not actually reserved even for that function. So this is, I'm a little worried about this for safety. I would think, if you're asking me, I would say every time you have a local variable, always reserve space on the stack for it. But they're not doing that. They're using space that's not reserved for that stack frame as a temporary scratch pad. And it's working, but that's the kind of shortcut that makes me a little nervous. Anyway, we see what it's done. So it's put this 28 on the stack. And so now we can continue and get to the next function. Now we're going to get in adder. All right, here we are at the start of adder, and we can look at RSP and RBP again. And again, these are the calling functions. This is mains, RSP and RBP, and that's important because it means the stack frame of adder, this is the same prelog, is going to be the same stack frame as the one, as the assign function. So if I examine the memory here, okay, there we are, and there's the 28 left over from before up here. And so now if I move forward again at next I, 4, and disassemble again to see where I am, I'm now down here, so I have taken data it found on the stack and put it in EAX, which the function assumes have been placed there by the calling function. The calling function is supposed to push arguments on the stack and then call this one. But it didn't do that. It just called this without placing arguments on the stack. So it uses whatever it finds on the stack as if it was, and so it's finding something left over from a different purpose. And then it's going to, so we now see the new stack frame is here, is the same place, 340 and size 0. And if we examine the memory, we'll see that 28 up there. And that is at RBP minus 4. RBP is here, 340, and I take away 4, and I get to 33C. This is the 32 bits starting at 340, and this is the bits before it. So when it went up here, where a parameter should have been, it found this. And so I guess I shouldn't be too upset. This is how parameters are used. Parameters are pushed off the end of the current stack frame where they'll be found by the calling function and copied in. That's the idea. Anyway, that's what it did. All right. All right, and then you got fancy stuff like you can have recursion. Here's the recursive summer where I'm trying to sum all the numbers up to n. So what I do is if it's 0, I return 0. Otherwise, I call summer of n minus 1 and add n to it and return it. So this will call the function over and over and over to make multiple copies of this function in memory as it runs. And I think we saw this last time. We saw how it goes. As you run this, it's going to make a series of stack frames up here. I don't think I need to do it again. It's the same in 64 bits as it was to 32 bits. Every time it re-enters the function, it creates a new stack frame and does the same commands on the different stack frame. And so you end up, if to doing the sum up to 4, you're going to end up with 4 copies of the function, all running in memory, all returning, all drawing from the same commands. All right. And there are arrays in assembly. In C, you declare something like int array 10 or int star array 10, and that will create an array. You typically have RDX contains the address of an array. This is a typical way you would do it. It doesn't have to be, but for this example, RDX is the start of the array. RCX is the pointer pointing to the element of the array, and RAX is the data. So if I set x equal to array in C, that's going to be getting the pointer int star. That's going to move RDX into RAX. It's an address. Here I'm going to get the value, so that's going to be the contents of RDX in EAX, with the parentheses indicating memory location here. Here I'm going to do array sub I, so I'm going to do RDX plus RCX times 4, because I've stored integers here, and they're 4 bytes each. Here I got the pointer to array 3, so I go to C plus RDX, and then I load the effective address to put here. Like I say, that is the use of this LEA function, which is a little screwy. I would just take RDX plus 12 to go to RAX, but this is how they do it. And here's X is array plus 3, which should be the same thing. It is. This is the, when you add to a pointer, it adds that many variables of that many blocks of the correct size, knowing what it is in C. So it doesn't just add 3 bytes, it adds 3 whatever you've stored here, and these are ints, so they're 4 bytes each. So it's 3 times 4, or 12 bytes, which is C in hexadecimal. And here we get the pointer of array plus 5, so that's 14 going to RDX. Because this is hexadecimal, 10, that's 5, right, because 10 is 4 4s, it's 16, and another 4 is 14. So 14 in hexadecimal is 5 4-byte words. Or you can say 16 plus 4 is 20, it's 20 bytes. So that's how you point your way to an array. All right, and so here you got an array with 10 integer elements. They're all 4 bytes long, like we said. And so this memory location starts at 0, this one at 4, this one at 8, and so on. All right. And they have matrices. You can have two-dimensional things. I wonder how other high-level programs do garbage collection. Well, garbage collection is pretty complicated. I know garbage collection is actually pretty interesting. As far as the one I know is operating system garbage collection. There is, I did actually a presentation on this at DEF CON. SSDs. have a property. Now, magnetic hard drives, you store data on them and you just leave it there. And when you want to store fresh data, you just write on top of the old data. But SSDs don't work that way. SSDs have a slow erase cycle, and you have to erase a block before you can write to it. So when you store files on an SSD, while you're not using it, it is trying to optimize the SSD. It's trying to gather all the empty space to form a large block and then erase that large block all in the background without you doing anything. And that they call garbage collection. And this has an amazing effect. You can store data on an SSD and you can read it. And then if you get an SSD that is performing garbage collection, you can read the data like every 1 second, and after 15 seconds, it's gone. It's like magic. So this has two effects. It's sort of interesting that way. And the other effect is for computer forensics. If you store data on a magnetic hard drive and delete that file, you can recover the file if you haven't written over it. But this is not true of SSDs, like an iPhone. Almost all the time when you store something on an iPhone and delete it, it's gone because garbage collection gets it and erases it. It's usually cannot recover any deleted files off an SSD unless the SSD is not performing garbage collection, which can happen if you do something like buy an off-brand SSD and install it in your tablet or phone and it doesn't really have the right driver, something like that. But anything modern is doing garbage collection, and that means all the data that is no longer in use is pretty much erased right away, except for small fragments that are usually not worth anything. Anyway, there's matrices. There's also structures in assembly. You can make a structure like this, 64 characters of a name, then an integer for name and grad year, then a float. You can make these structures. One thing about them is, in this case, you had 64 for the name, so it's going to work nicely. And you can refer to it in an assembly. It's exactly the same as 32-bit. We talked about this last time. Everything goes to an offset. One thing about it is, if you had a 63 character name, then you would have to have a padding byte here because there are rules. 2-byte data has to be starting on a 2-byte boundary and 4-byte data has to be on a 4-byte boundary. So if you have an odd number of things stored before it, you'll have to add a padding byte here. All right. And then there's buffer overflows. And I see we've been here for more than an hour. So let's take a break. It's 7:04. Let's take a break until 10 after, and then we'll continue here.